Hello friends, here I am back with some interesting numerical questions from general pharmacology which have been asked in previous NEET PG entrance exam. And I would also like to tell you that here I am not going to discuss the questions which are solely based on the basic formulas where just by putting the different values in the formula you immediately get the answer. Rather, the questions which will be discussed today are a bit tricky and you need not only the formula but also you need to use your wits and analyzing power to solve these numerical problems. And here the numerical questions have been divided into two videos, and this is the first video of this section. After this, the second video of the numerical questions will be uploaded. So without any delay, here comes the question number 1. Calculate the therapeutic index of the drug from given DRC. Here is the DRC of a drug, and option A is 8, option B 16, option C 128, and option D is 1024. So here in this image, the first DRC indicates the DRC of the therapeutic effect, and this graph indicates that ED50 is 8 mg, because here 8 mg is the dose which is affecting or which is producing the desired response in 50% of the experimental population. Since toxic effects are the different types of effects, so we need a new graph to study these effects. So in the second DRC, toxic effects of the drug have been shown. And here we can see that median toxic dose, that is the dose which is causing a particular toxicity in 50% of the experimental population or animals, is 128 mg. So the therapeutic index, there is LD50 by ED50, or we can say TD50 or ED50 will be TD50, that is 128, by ED50, that is 8 mg in this question. So 128 divided by 8, that is 16. So the therapeutic index here is 16. So the option B is correct here. And you should also know that in case of humans, we use TD50 in the formula instead of LD50 because death is undesirable in case of human trials or experiments. However, in this question, the experiment has been done on animals. Still, the DRC of toxic effect has been shown here and not of lethal effects. It means sometimes in case of animals also, the formula of therapeutic index may be TD50 by ED50. While LD50 by ED50 is commonly used in animal studies, TD50 by ED50 can be more relevant in specific contexts where lethality is not the primary concern and toxicity at sublethal levels is more pertinent. For example, number 1, chronic toxicity studies. In long-term studies, chronic toxicity, that is TD50, rather than acute lethality, that is LD50, may be more relevant. This is because the focus is on understanding the effects of prolonged exposure to the drug. And second example is non-lethal adverse effects. If a drug causes significant non-lethal adverse effects that impact the animal's well-being or study outcomes using TD50, that is the dose at which 50% of the population experiences a defined or particular toxic effect, can be more appropriate. And the third example is ethical considerations. To reduce animal suffering, researchers may prefer to avoid studies that determine lethal doses and instead focus on doses that cause significant but non-lethal adverse effects. And fourth example is comparative studies. When comparing safety margins between different species of animals or translating data from animals to humans, TD50 by ED50 can provide more relevant information as it avoids the extremes of lethality and focuses on more clinically relevant toxicities. Now coming to the second question. Which of the following statements about the given plasma concentration versus time graph is correct? Option A is Tmax of the drug is 3 hours. Tmax is the time required to attain maximum concentration, that is Cmax. Well, Cmax is the maximum concentration obtained with a particular dose. It is 120 mg per dl in this graph. Now, option C. Elimination half-life of this drug is approximately 2 hours. So here, never get confused about the term elimination half-life. There are two types of half-life. One is distribution half-life and another is elimination half-life. Distribution half-life is calculated once the drug is undergoing distribution within the body. After the distribution, drug is metabolized and eliminated from the body. So the half-life during this elimination phase is known as elimination half-life. And at the UG level, you have to study only about the elimination half-life. So in your textbooks, whenever the term half-life is used, it means to say authors are talking about elimination half-life. And here in this question, at 3 hours, concentration of the drug was 100 mg per dl, and at 5 hours, it becomes 50 mg per dl. So 5 minus 3 equals to 2. So 2 hours is the half-life in this question. And option D is the graph can be used to calculate ED50. So, well, ED50 and LD50 are calculated from DRC, not from concentration time curve. So, this option is not correct. So, elimination half-life is 2 hours. This option is correct. Now, here comes the third question. A patient was administered 200 mg of a drug. 75 mg of the drug is eliminated from the body in 90 minutes. If the drug follows first order kinetics, how much drug will remain in the body after 6 hours? Option A is 30.5 mg, option B is 12.5 mg, and option C is 25 mg, and option D is 50 mg. So, well, here the initial dose is 200 mg and 75 mg is eliminated in 90 minutes. It means to say that 75 by 200 into 100, that is 37.5. It means 37.5% of the drug is eliminated in 90 minutes, that is 1.5 hours. So, after 1.5 hours, remaining amount of the drug will be 200 minus 75 equals to 125 mg. And we know that in first order kinetics, a constant proportion is eliminated in unit time. So we can say that in next 1.5 hours, 37.5% of 125 mg will be eliminated. It means to say 125 upon 100 into 37.5 equals to 1.25 into 37.5 equals to 46.875 mg will be eliminated in the next 1.5 hours. So now 125 minus 46.875 equals to 78.125 mg will remain. Now here we can see that 1.5 plus 1.5, that is after 3 hours 78.125 mg is remaining. Okay, and now after next 1.5 hours, 37.5% of this 78.125 mg will be eliminated. That is 78.125 upon 100 into 37.5 equals to 29.29 mg will be eliminated. So we can say that 78.125 minus 29.29 equals to 48.83 mg will remain. It means after 1.5 plus 1.5 plus 1.5, that is 4.5 hours. After 4.5 hours, 48.83 mg of the drug will remain. And now, in the same way, after next 1.5 hours, 48.83 upon 100 into 37.5 equals to 18.31 mg will be eliminated. So, 48.83 minus 18.31 equals to 30.52 mg will remain. So we can say that after 1.5 plus 1.5 plus 1.5 plus 1.5, there is after 6 hours. So after 6 hours, 30.52 mg of this drug will remain. So we can see that the option A is correct here. Thus, we can see that it was a very tricky question and it required a good deal of calculation also. But you should also be ready for these types of questions because this question has been asked in AIMS May 2017 exam. Well, anyway, here comes the fourth question which was asked in AIMS November 2016 exam. The question is, digoxin has a half-life of 40 hours. It helps to determine option A, regimen for smooth discontinuation. Option B, need for loading dose in order to get immediate effect. Option C, regimen for maintenance dose. Option D, single dose will work for 40 hours. So here we know that loading dose of a drug is required for those drugs which have high volume of distribution like chloroquine, or with the drugs which have long half-life but the action is required quickly like digoxin. So here half-life of digoxin is 40 hours and we know that steady state reaches in 5 half-lives. And yes, why does steady state is attained in 5 half-lives? This has been very clearly explained in my previous video, Plateau Principle, and link to that video has been provided in the description box. So you can go through that video also. Okay, well, so as we have discussed that steady state reaches in 5 half-lives, hence we can say that it will take 40 into 5, that is 200 hours for digoxin to reach the steady state plasma concentration. And as we require it to produce action quickly and we cannot wait so long, so a loading dose is given to achieve steady state quickly. So the option B is correct here. Now coming to the fifth question based on the effect of the pH on absorption. Cimetidine is a weak base with pKa of 7, and how much percentage of cimetidine can be absorbed from the stomach where the pH is 3. So it will be difficult for the drug to cross the plasma membrane and less of the drug will be absorbed. According to Henderson-Hasselbalch equation, we know that one scale change in the pH will cause tenfold change in the ionization. For example, if the pKa of an acidic drug is 5, then at pH 5, 50% of the drug will be ionized and 50% of the drug will be unionized. Now talking about the one scale change in pH. Suppose that pH becomes 6, that is more basic than pH 5. Now this acidic drug is getting a basic environment. So this drug will be ionized and ionized portion will be more than the unionized portion. So at pH 6, 90% of this drug will be ionized and only 10% of this drug will be unionized. Now again, if the pH becomes 7, that is more basic than before, then ionized portion of this drug will be 99% and unionized portion of the drug will be 1%. Similarly, at pH 8, which is more basic than pH 7, the ionized portion of this drug will be 99.9% and the unionized portion of this drug will be 0.1% only. So here we can see that 1% is 10 times smaller than 10% and 0.1% is 10 times smaller than 1%. That's why we used to say that there is 10 times or tenfold change in the ionization. So we can see that one scale change in the pH, that is 5 to 6, 6 to 7, 7 to 8, is causing tenfold change in the ionization. Tenfold change means 10%, then 1%, then 0.1%, and then 0.01%, and so forth. And if we are talking about the same type of changes in the pH with a basic drug, the case will be converse. That is 10%, 1%, 0.1%. These will be the portions of the ionized form instead of unionized form. Here we can see that the medium is gradually becoming more acidic. So more and more of the drug portion is becoming ionized because the drug is basic. And now pH 3, as asked in the question, 99.99% of the drug will remain ionized and 0.01% will remain unionized, which will be absorbed. And now here is the sixth, which is the last question of this video. A patient requires infusion of procainamide. Its half-life is 2 hours. Infusion is started at 9 a.m. and at 1 p.m. on the same day, the plasma concentration is found to be 3 mg per liter. What will be the steady state plasma concentration after 2 days of infusion? Okay, now just listen. From 9 a.m. to 1 p.m. that is after 4 hours, and 4 hours means 2 half-lives because half-life of the drug is 2 hours. And we also know that after 2 half-lives, 75% of the steady state is attained. It means in this question 3 mg per liter concentration, which is attained after 2 half-lives, is the 75% of the steady state. So steady state concentration will be 3 upon 75 into 100 mg per liter, that is 4 mg per liter. And as per the plateau principle, we know that steady state is attained after 5 half-lives. It means after 2 into 5, that is after 10 hours, this steady state, that is 4 mg per liter, will be attained. And in this question, they have asked about the steady state after 2 days. So here you should know that 2 days don't matter here, whether it is 2 days or 3 days or 4 days. The main thing is after 10 hours, that is after 5 half lives, steady state, that is 4 mg per liter, will be attained. So this was all for this video, and soon I will be back with the second part of the numerical questions. And if you have any queries, you can write it down in the comment section, or for this purpose, I have provided my email ID also in the description box. Stay connected and thanks.